Not having videoed. Please speak up.
For part D,
Yeah.
how do you use constant rate reasoning to interpret the vertical intercept?
Oh, I would say watch the video because we already did it, but I don't have a video. So it's the same thing we do. You start with delta x. Delta x is -7. Here's the constant rate of change reasoning. Changes in percent are always a constant times the changes in the minutes. Right? That's this, this thing right here. That's your constant rate of change reasoning. Changes in the one quantity are always a constant multiple times changes in the other. So you would take that -7 times -3.1, and it would give you an increase of the percent. That's your constant rate reasoning. You're using this changes in y are always -3.1 times changes in x. Okay, other questions about this example? Does it help? Okay, good. So this screenshot's on the video, so you can recreate it with your own explanation. All right. So where are we here? We need to talk next about piecewise linear functions. It's our next topic. So everything that we're doing is very intentional. Ideas you should see ideas coming together in groups. We're building all these building blocks to get to building up these, the calculus, right? So the calculus is really about when the rate of change changes. Okay, so that's most relationships in life of two quantities are where the one quantity, its rate of change changes with respect to the other. Okay, but in order to do the modeling and to build it up, we absolutely need constant rate of change to do it. So now we're going to take our first step towards changing rate of change, but we're still going to be working with constant rate. Okay, so a piecewise linear function means a function has a constant rate of change, but it has different constant rates of change over different intervals. So a certain interval you have a constant rate, and then you have a new interval. It's a new constant rate. So this begins our transition towards changing rate. You see? But we're still talking about constant rate of change. So here's an example we can work through here. I'm going to write this down. Actually, this is going to be in your reading and assignment for Wednesday, so we don't copy all this down. So suppose you're on the highway driving from Atlanta, Georgia. You set your cruise control at 60 miles per hour. 1 hour and 15 minutes later, you are 120 miles from Atlanta. Okay? At that time, you change the cruise control setting to 70, and you go that speed for another 45 minutes. So we want to come up with a function that gives distance from Atlanta as a function of the number of hours since you initially set the cruise control. So do you see how that example fits this model here? Do you see that? That we have a constant rate of change over, hour and 15 minutes? And then we have a new constant rate of change for the next 45 minutes. Okay? So this is the idea of we'll have to come up with what's called a piecewise linear function. So let's start by sketching a graph. So same thing there. So let's start by sketching a graph just to get a feel for what's going on, and then we'll get into the math a bit. Wow, these are the worst lines I've drawn all day. So one more time. Better. Okay. All right, so when we turn the cruise control on, are we in Atlanta?
No.
No. How far from Atlanta are we? 120 miles. That's when I turn the cruise control on, 120 miles? Brent?
Like an unknown.
Yeah, so we're just somewhere. It just says we're on the highway, right? We're on the highway leaving Atlanta or somewhere. And then what do? So then we turn the cruise control on, and what's our change in time?
Hour and 15 minutes.
Hour and 15 minutes. So in hours, that is 1.25, right? And at 1.25 hours, what is our distance from Atlanta? 120, right? Okay, so we have a point. Okay, and that is the point 120, 1.25. Nope, other way around. Thank you. Yeah, thank you. So at 1.25 hours, we're 120 miles from Atlanta. Okay, how did we, so from our, when we turned the cruise control on to there, what was our rate of change? Constant? Constant rate of change. They graph as, if you have constant rate of change, it graphs as a line. That's what we just did on, we focused on last week, right? And there, so there our K is, so in this interval here, K equals 60, right? All right, then the speed limit goes up, or no, who pays attention to speed limits, right? So I do. Okay, so something happens, and we're bored, or the speed limit changes, and we say, no, I want to go 70 now. And I go 70 for another 45 minutes. That puts us at the 2-hour mark. And what happens? So it's going to be, right, so now the relative size of changes in D to changes in T is greater. So what will the resulting line be? Steeper line, right? Something like that. Okay. Cool. So we've got 2 linear functions to come up with. So what we can do is we can call this one F1, and we can call this one, the name of it, F2. So can you use point slope form, so this is this form we're working on, we just summarized in the past slide, to write F1 and F2. See if you can do it. To write, and I'll call on someone in a second, F1 and F2. You don't have to, so you can just use the point slope form. You don't have to do any, you don't have to go through the process of delta x, delta y, and then old y, or new y equals old y plus, you can just use it. If you understand it, now we can just use it. So anyone, because there's no calculations to do, anyone want to give it a shot? So F1 of t.
Will you, y minus 120 equals 60, parentheses 1.25, actually x minus 1.25?
Let's get that. What is the point slope form? Y equals B
plus B.
So just because we're gonna just now use it, don't forget the meaning, okay? So don't forget where it came from. So that building that up is important. You still need to know how we built that up. But now we can just use it. So was that, Kevin, was that what you were saying? Kind of.
So is
Nicholas.
y equal to 120 plus 60 times the quantity of x minus 12 and a half.
So he wants 120 plus
60 times the quantity of x minus 12.5.
how do you do? Does it work?
Oh, 1.25, my bad.
You might have said that right and I just wrote it wrong. Okay? Now, when we write F2, so what can we do for F2? Yeah.
Why is 120 shouldn't it? It should be 120 because it doesn't intercept the y-axis. 120 intercepts the better value.
Okay, so she's saying this is not the where it intercepts the y-axis, so it shouldn't be 120. Melody.
Isn't it if you factor it out 60x minus 1.25 eventually you get the y-intercept, so it doesn't really matter?
So going back to our form here, what is A, B? What is that?
Just one on the line.
Any point on the line.
Yeah, I didn't use the y equals b plus that formula. I used the change and exchange y to get that.
What
I
is?
didn't use that formula. I did it the way we did on the homework problem with the.
Those are the same. Well.
Oh, and I'm just saying that's how I got 120. If that's what people were wondering.
So AB is any point on our line, and so we're using this point as AB. Okay, so we're using AB as a point right there. And so B is the y value, 120. Does it have to be the y-intercept? Do you see it now?
Yeah.
You better? Okay, cool. Yes, that's right. Okay, so we got that. And then what about F2? Okay, right. So we can still use that same point plus. Now it's going to be 70 times. Okay? So how could we, and so I should have left room over here, but basically we're putting this all together as one function, f of t equals, so we've got, this is how we write it piecewise, 120 plus 60 times x minus 1.25. And that's from, so now we got to specify, this line goes on forever in both directions. We have to specify what part of that line we want. And that's kind of like our graphing calculator assignments. So we want x to start at 0. To 1.25. Okay, so that's how we specify. We've got that line, f1, and we only want the part of it that starts at t equals 0 and ends at 1.25. All right, so now how could we use f1 to write f2? What is 120 in terms of f1? It's f1 of what? 1.25. This is a technique we're going to use. That's why I'm introducing it. So you can write that starting value of the new line as the y value of the old line at the ending point x. You see that? So this 120. So this is the old, or the starting value of y for the new line. Okay. So plus now 70 times x minus 1.25. So you notice we're using function notation here. And this forms an ordered pair. Your input value and the output value of the starting point, which you get that output value from the previous function. You see that? From the previous f1 up here. Okay, and that's from what to what? Right. So that's going to be something we want to do right there, is write the starting y value of a new piece as the ending y value of the previous piece, right? So you take that x of 1.25, plug it in there. We can represent it this way, and that's that y value. We know it's 120, but sometimes we won't, okay? So this is a piecewise function that gives us the distance from Atlanta.
Shouldn't
Yeah.
the 1.25 be like just less than or equal to x?
Thank you, yes. We can't do, yeah. So we can choose to do it either way, but the way we choose to do it is we're going to include it on this one, and then when we start the next one, we're going to start strictly greater than 1.25. Yeah, thank you. But then this one has to equal to there. Yeah?
How do we take this in our graphic?
We'll get to that. So that's coming in the next. So, well, your assignment for Wednesday, we'll just more practice of this, and then we'll get to graphing calculator. I'm going to try to post your assignment right now in the next half hour. Oh, sorry. Recitation this week. You will have a quiz on this new stuff since the test. Yes, quiz and recitation.
So this is going to be in recitation and mark
What?
that we just did?
Yep.
Okay.
Yep. Oh, thank you. I don't think. No, there's not. They can't. They don't do it. They don't have it for Linux. You be able to adjust anyway. Okay.